Greg has done a whole bunch of things over the years, including writing several books about programming and software. And he started Software Carpentry, which is a great organization that teaches researchers how to use computers. And as of recently, Greg works for RStudio, and I'm curious to see what he will do there. And he will today tell us how to make a hard-boiled egg.
Okay, thank you very much, Ariel. I'll check with the AV team. Audio's good. Are we happy? Okay, ladies and gentlemen, please, a round for the AV team. They never get the recognition they deserve. Thank you very much. Okay, so that's me. That's my email address. The talk is CC by. Please quote, tweet, whatever. Just provide a link back. Okay? And this is where the title comes from. For my money, Terry Pratchett was the funniest man writing in English in the post-war years. I met him 3 times. It's not often that I struggle to get a word in edgewise. I was very sorry when he passed away. My younger brother was fond of saying that happiness comes from having high hopes and low expectations. And I am trying increasingly these days to lower my expectations so that I can accomplish more of my goals. So what I'm going to talk about today is a plan that I think is actually feasible for significantly improving software engineering education and making the world a better place. Please note those are not necessarily the same thing. You are, as an institute, uniquely positioned to implement all of this. I expect great things from you. Okay? Come on in. Ladies and gentlemen, Andy Lumsdaine. Give it up.
Drawing attention to myself.
There you go.
I need that for my...
So here's what I'm building on. Veronica Cheplagina, who's a professor in the Netherlands, introduced me to the idea of weak failure, which is I tried really hard and nothing much came out of it, and strong failure, which is I tried really hard and I actually inadvertently did harm. I've had a few of those, but mostly what I'm talking about today is built on several weak failures that I hope I've learned from. Things that I put months or years into that didn't accomplish what I set out to accomplish. So I have stepped on landmines you don't need to step on. I've explored paths that lead nowhere, and I'll be talking about those in the hopes that it can direct you towards something more fruitful. So once upon a time, there was a magazine called Dr. Dobbs Journal. And most of you are too young to remember it. For a period of about 20 years, most professional programmers were reading this. It was pulling together stories and ideas and articles. We printed them back then, right? It wasn't just online. And I became the book review editor. And over the course of many years, I got to look at literally hundreds of books on compilers. Every time some publisher had a new book on compilers, it would land in my mailbox. Nobody ever wrote books about debuggers. There are right now available on Amazon 3 books about how to design and implement a debugger. 1 of them is useless, 2 of them are wrong. Now, I want you to think about what's wrong with our education, that we are spending all of this time on how to create programs and none on how to fix them. Right? There are gaps in our curriculum. How many of you have ever taken a course on debugging? So far as I've been able to find, none of the top 100 schools in the United States or Canada offer a course on debugging. And yet, as a professional programmer, you will spend somewhere between 25 and 75% of your time fixing broken code. Right? There are a couple of good books on debugging, but we don't teach this as a first-class art. It's puzzled me. We also didn't teach people the design, implementation, and use of build tools, of package managers, of all of this stuff. And so here I am, having worked in industry for 20 years, being brought into the University of Toronto to help revise their software engineering curriculum, and there's nothing on Amazon that will help me teach the things that people actually do. So I thought, great, I will fix this. Let's start with the course on software architecture, CSC 270. 24 books. And what I found was, out of those 24 books, there was a grand total of 12 pages describing the architectures of actual software systems. Right? So 24 books, 300 pages each. We're looking at well clear of 1,000 pages of material, much less than 1% saying, and by the way, here's an actual piece of software. There were more pages in those books on the importance of eliciting requirements than there were on how does the stuff you're using today actually work. If you were going to hire an architect to redesign your house, and they had looked at 1/4 of one blueprint over 4 years, you would probably go and find another architect. And yet, we take this as normal. So I thought, great, I can fix this. So I organized a series of books. I invited a bunch of programmers to tell me about the most beautiful piece of code they'd ever seen. This book did reasonably well. We then followed it up with a series of books in which we got the authors of some widely used open source packages to describe the architectures of their systems. The first two in this series, between them, describe 50 widely used open source packages and explain their design. One of the interesting things I took away from that was that in the majority of cases, unprompted, the way the architect describes the system is by recapitulating its history. The only way you can understand the design is to understand how we got here, because this is a solution to a problem that you don't even realize exists, because this works well enough that you've never run into the problem. Right? None of the architectural design notations promulgated by software engineering researchers allow you to represent the evolution over time in any comprehensible way. Okay? This seems like a research opportunity. Hands up those of you in CS. Okay, you have a thesis topic. I look forward to great things. Right? I also learned from this notion of countervailing currents. If practitioners are going to teach researchers what architecture actually is and how best to describe it, it's only fair that the researchers should teach the practitioners what they actually know and why they believe it. So we pulled together another book where we got leading researchers in empirical software engineering to explain some of their favorite findings. What do you actually know about the way software is built, and why do you believe it's true? For example, how many of you know the work of Andy Stefik? Okay. Andy and his team are building a language that's meant to be accessible to the visually impaired. In order to demonstrate that it's actually better, they've been doing a series of beautifully designed studies on how easy it is to learn the notation of a programming language. Long story short, the languages in the C family, the curly brace languages, are as hard for novices to learn as languages with a randomly designed syntax. Their placebo was created one Saturday night by rolling Dungeons and Dragons dice to pull ASCII tokens out of a table to design the syntax of a programming language. It is no harder to learn that language than it is to learn C, Perl, or Java. Python and Ruby are significantly easier for novices to learn to read and recognize. And Quorum, which is the language they're building, is easier again because they A/B test every feature before it goes into the language. So they can shave literally months off the time it takes you to become proficient in programming by doing what video game designers and website designers and everybody working in UX has been doing for 20 years. And the reaction of the programming language community has been, la, 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 I can't hear you. Okay? How many people know about the Brown and Altadmeri work in the UK? There's a project called Black Box. They are collecting data from the IDE used in introductory programming classes in high schools all across England and Wales. What do you get when you analyze 23 million failed compilations of Java programs? The answer is the mistakes that learners are making have absolutely no correlation with the mistakes that their instructors think they're making. You go and you ask 200 instructors what mistakes do students make and rank them. And then you do the correlation with the mistakes you're actually seeing. And you discover that not only do the teachers not know what's going on, their understanding of novices' mistakes does not improve with experience. You can be a 20 years in service teacher and you don't know anything more about what's actually going wrong in your students' programs than you did the day they started. That data set, by the way, is publicly available if anybody wants to go download it and start doing their own analysis. They've got this enormous amount of data, and you don't even know it exists. This one has had me yelled at more than almost anything I've ever written, and I do tend to get yelled at a lot for what I write. How many of you use test-driven development? Write the test for, okay. As far as we can tell, test-driven development is no more productive than test after development. We have several studies, including 2 blind replications, that show that writing the tests first or writing the tests afterwards doesn't make a difference. Why then do so many people in the Agile community believe so strongly that it does that they will look up my personal email address to send me hate mail when I publish a report about these studies? Right? The answer comes from some work done 2 years ago by a group in Italy. They found, yet again, that TDD doesn't make a difference. But then they went back and did a second analysis of their data, because they did see differences in productivity between different programmers. What matters is the spacing. If you write code for 10 minutes and test for 10 minutes over and over again, you are more productive than somebody who writes 10 hours of code and then tests for 10 hours. It's the interleaving, the granularity of the interleaving is what makes a difference. At the same time as the Agile community was preaching TDD, they were also pushing people towards shorter cycles. It's the shorter cycles that have the benefit. We're misattributing the cause, and we have the data to prove that. That's interesting. Particularly interesting for me now that I'm working more with data scientists. I mostly can't write my tests in advance. If I knew what the right answer was, I would have shipped and moved on. But if I write my pipeline and then come back after I've seen it and add a few tests as sanity checks, I'm being productive, provided I'm doing that at fine granularity. Okay, that's interesting. That's an actionable result. And here's my favorite. I've got a few more here. Over a third of failures in data-intensive systems occur because the error handling code has never been tested. Okay? You can eliminate over a third of the crashes in data-intensive systems simply by having people test the exception handlers before they go into production. Okay? That's a result from Microsoft research from about 2014. This is an easy thing to check. Do you know what the most common exception handler is in Java code? Empty. Over half of exception handling blocks in Java code do nothing. The catch is there because the program won't compile without it. Okay, this is something our linting tools can check, right? I hate Git. Like, you have no conception of how much I hate Git. Git is the worst tool to teach I've ever had to put into a classroom, and I have taught people Emacs. Okay? And if you look at the work of Jackson and Perez de Rosa from MIT, it's awful partly because the syntax is so wildly inconsistent, right? But also because even experienced users have formed a mental model of its operation that is significantly different from what it actually does. Right? And they've got the in-depth user studies to show that a lot of expert users have evolved a similar model which is wrong. Any tool which encourages me to build a wrong model is a bad tool. Okay? And as I was saying to Valentina earlier, how many of you would actually like to be rich, famous, and popular? Okay, okay, excellent. Here's what you're going to do.
I'd like to be rich, famous, or popular.
High hopes, low expectations, right? Former tenured faculty is lower your expectations, son. Okay, here's what you're going to do. I want you to go to GitHub and download the histories of the 1 million most popular repositories. I then want you to mine those histories to find common subgraphs, small operations that account for 90% of everyday use. Some of us are old enough to remember programming with go-tos. How many of you have ever written a go-to? Okay, that was normal when I was your age. And in the 1970s, as a species, we thought, wait a second, we're all using the go-tos in more or less the same way. Why don't we just standardize on for loops and if statements and while loops, and then just stop using go-tos and stop getting into trouble? Git is the go-to of version control, because you can go from any node in the graph to any other as long as you don't create a cycle. There are no constraints. It is exactly go-to in assembly language. I'm willing to bet that the vast majority of people using it are using it in a small number of various stereotyped ways. We can mine those ways from their histories by looking for common subprimes in the graph, and then provide a version control system that only allows them to do that in the same way that languages like Pascal and Python and Java say there's only certain ways you are allowed to traverse the control flow graph. 1% of power users will scream blue bloody murder because there's this corner case over here, and everybody else will say, thank you, here's my money. right? This is a pattern we have seen over and over again. Structs with function pointers morph into classes because the more restraints we put on you, the further you can go. We're just going to take away problems that aren't productive. And we've got the data, and I think there are people in this room who actually know enough data science to mine graphs looking for common subgraphs. All right? You build this tool, you become the Java to Git's C++. And you've instantly made a few million friends because you've created something that doesn't blow up in its diaper on people's desktop over and over and over again. I'm an experienced Git user. Ask me what I was doing at 6:30 this morning. Yes, that's right. rm-rf followed by git checkout. Hands up if you've ever jennied a repo. Right? Okay. This is the most interesting result for me of the last couple of years. Elizabeth Petitsis and others did a double-barreled study at the University of Toronto. A lot of computer science faculty and a lot of people in industry still claim that there's a geek gene. Either you get it or you don't. So, part one of the study, go and grab the grades for 270 introductory programming courses and analyze them. If there is a geek gene, if some people get it and some people don't, you expect a bimodal distribution. The distributions are unimodal. There is no evidence that there's two communities in the classroom. By itself, that's an interesting truth, but here's the second part. I am going to randomly generate samples with small n, 50, 100, something like that, from a normal distribution, and I'm going to take it to a computer science professor and ask the professor, is this unimodal or bimodal? If I tell the computer science professor the distribution is from a CS class, they are far more likely to see it as bimodal than if I tell them it's from any other course. They're seeing their prejudices and beliefs in the data. Prejudice shapes perception. And we know from the Lemin work and others in the 1970s that as soon as you believe there are two groups, it becomes a self-fulfilling prophecy because you focus your attention and reward on the people that you believe are in the group that gets it. And you tend to give less time and energy to the people who don't, and so it just perpetuates itself. Walk around any undergraduate CS classroom, and I think you are seeing the effects of the conscious or unconscious belief that some people get it and some people don't. She got yelled at for this one, but the research is rock solid. Beautiful, beautiful result. So, weak failures. To first order, the books that I worked on architecture and on empirical results in software engineering have had no effect. They consumed between them several years of my life, and they're not part of the undergraduate curriculum. They have not changed what we do to teach or train people. We don't teach science to computer science students, and I can illustrate this. I'm Canadian. Any other Canadians in the room? Secret handshake? Okay, so in order for an undergraduate biology program at a university in Canada to remain accredited, students have to spend 6 hours a week in the lab, on average, over the 4 years. Right? You actually have to learn how to do science. How to set up an experiment, how to collect data, how to analyze it, how to compare it to a model. Many of you did science degrees as undergrads. You spent time in the lab, right? The average computer science student at the University of Toronto or the University of Waterloo does one experiment in 4 years. Usually in the operating systems or networking course. Collect some performance data, throw away the outliers, draw a straight line, hand it in. That's your exposure to science. So it's hardly surprising that they don't understand what science is or how to do it. It's equally unsurprising that they don't value it. So after teaching programming to scientists for the last 20 years, I've come to believe that science is a good thing. I've been infected by the scientific method. I actually got into empirical software engineering research because every time I taught a software carpentry workshop to a bunch of physicists and said, here's how you should program, sure as hell a hand would go up and say, citation, please. Why do you believe that? What's the evidence that that practice actually makes a difference? Gosh, that was embarrassing, right? What I now believe is that the math that is going to put the engineering in software engineering isn't the discrete math, isn't the formal logic, that I thought it was years ago. It's not proofs of program correctness. The math that is going to turn software engineering into an engineering discipline is statistics, and you are going to help me get there. Okay? The problem is the curriculum is full. I would love to teach undergraduates in computer science how to do all of this. How to get data and analyze data in order to verify or disprove a hypothesis about software or software development. Are long functions likelier to be buggy than short functions? Yes. What if you normalize by length? Are they likely to be buggier per line? The answer is still yes, but the effect is weaker. In some languages. In other languages, it turns out that the bugginess per line seems to stay constant regardless of the length of the method. Think about what you have to know in order to be able to answer a question like that. Program analysis tools, check. Statistics, check. Building a model and checking the model. You have to do science. I want undergrads in software engineering and computer science programs to think that doing this kind of science is normal, because I want them to be able to look at a claim about test-driven development and say, citation please, and then understand it. I want them to check all the folklore that's being thrown at them about how to program, about this language being more productive than that, about everything, and be able to fact-check it. In the same way that if you've done a degree in physics and somebody comes up to you with a perpetual motion machine, you can say, excuse me, right? That's a better world. So, the problem we face is that the curriculum is full. In 2009, Toronto District School Board voted unanimously to introduce programming classes in high schools. Here we are 9 years later and it hasn't happened. Why? Because they couldn't agree on what to take out to make room. Hand, please.
So I was at a presentation by the Code.org folks yesterday, and they pointed out that there is only one job in America that requires that you be able to actually do long division, and that is elementary school teacher. So there's the stuff that could be removed from the curriculum, we just don't want to remove it.
Everything that's in the curriculum has an entrenched defender. If you take a look at an undergraduate program in organic chemistry, every single one of those required courses is not just the pet of somebody senior to you with tenure. That person genuinely believes that this is the most important thing in education, and they will fight tooth and nail to retain it. In Toronto, there was a very serious proposal to remove math education from high schools to make room for programming. Because mathematicians don't get jobs, but programmers do. Well, that one was defeated. The second proposal was to remove health education. Let's not bother teaching kids about obesity and why they should put on a condom. Let's just make them all programmers. I don't like this as a future, right? The problem is, where do the rooms come from? Where do the teachers come from? Where does the teacher training budget come from? All right? We really do have a zero-sum game, and that's a constraint that we just have to live with, right? I also feel, and this is a personal choice, we ought to be trying to help everyone, not just CS majors. Right. I think everybody in this room would agree that the skills that are involved with this machine are something that everybody now needs, regardless of what field they're in. I want a level playing field. I want everybody to be able to compete. I constantly have to gear shift when I come down to the United States and remind myself that you still measure things in body parts. Right? The rest of the world has got a thing called the metric system. But when I'm in the United States, I will quote distances in miles and yards and feet and inches, because that's what you all use. Right? When I'm in England, I will insert an extra U into almost every word, more or less at random, so it looks like British spelling. Right? So if we want to get the kind of change that I want, how can I do it within the constraints of the system that we have? And this is a big shift for me, because for years what I was trying to do was change the system whole scale. Right? Let's just burn it all down and start over. Having been involved with MOOCs and other things, I now realize just how damaging that is. Move fast and break things breaks things. And the things you're breaking are people, their lives and their careers. So I'm now looking for evolutionary solutions. So it's either got to be something you already know, or it's got to be something that you can pick up in one bladder of hands-on instruction. And in case you're wondering about my use of the term bladder, the basic unit of teaching is the bladder. Right? This was pointed out to me by a very pregnant woman in one of my classes. And I said, gosh, I've never thought about that. And she said, you've never been pregnant. Okay? So you've got an hour. What can you do? What are our choices today? If I want high school students to be exposed to data and data wrangling and statistics so that when they arrive in undergraduate, they will know enough that we can immediately start doing science with them. Choice number one is this functional reactive language with an intuitive interface, otherwise known as Excel. I love spreadsheets. They are a beautiful tool, and it's time that people with CS degrees stopped sneering at them. And as a footnote, I have got a standing offer of a bottle of wine, a really nice bottle of wine, to anybody who can show me that these are more error-prone or less reproducible than writing text. The data to show that spreadsheets are less good than R or Python does not exist. Because I want to normalize by, for example, probability of error per published result, or probability of error given number of hours you've invested in mastering the tool. Jake, raise your hand, Jake. Jake knows a lot of Python. If he had invested all of those hours in becoming an Excel wizard, my bet is that he would probably do very good science in Excel. Right? I think that programming languages probably take you further, but in the hands of people who are primarily focused on doing other things, I bet that this is an equally good tool. We dismiss it because it's usable. I'm willing to be proven wrong, but nobody's done that study. If you do that study, it doesn't matter what the result is, it will be publishable, and people will yell at you. So get to it. Right? If you're not making people angry with your research isn't worth doing, right? Here's a programming language. You can tell that CSS is also a programming language because it needs to be debugged. I don't know why the box doesn't line up the way it's supposed to, right? It's a beautiful view, and I do believe it takes you further, right? But it's a very, very steep hill for people to climb. Can we do better than this? The answer is yes, we already have. How many of you are familiar with Scratch? Scratch is, for my money, the most important invention in computing in the last 25 years, because it's proof by example that you can make imperative programming accessible to 6-year-olds. You can also make it appealing and engaging to that audience. How many of you have kids? Have your kids played with Scratch? It's beautiful to watch a 6 or 7 or an 8-year-old start to build video games by dragging blocks out and experimenting and doing all of those things that Seymour Papert said we'd be able to do. Right? And you don't have to explain the interface. In an hour, you can teach kids or adults everything they need to know about how to use the interface, how to assemble programs, and after that, they're actually focused on the computational thinking. They need to learn why sometimes loops are infinite and sometimes signals don't get caught, and so on and so on. But that's the stuff we want to teach. We don't want them wasting their time with curly braces and indentation and package loading and things like this. Right? This is a beautiful tool. Multiple studies have shown that people learn programming and the thinking behind it faster when they're using a blocks-based environment than when they're using text. This is now scientifically a settled issue. Right? It eliminates the pointless syntax mistake. It's got the obvious affordances. You can see what fits together and how to use it. And by the way, it plays well on touchscreen devices. It's a hell of a lot more accessible, both for people with disabilities and for people who are economically disadvantaged, than something that requires a lot of typing. Right? I strongly believe that 5 years from now, most Internet of Things devices will be programmed on a little touchscreen where you're dragging out blocks. Your fridge, your PVR, your car, the way that you will tell it what to do is using this interface because everybody will know it. If you are under 20, Scratch was probably your first exposure to telling a computer what to do. So if I am an auto manufacturer, if I am Maytag making a washing machine, if this is the interface I present to you, I didn't have to teach you anything. It works the same way everywhere, and you can just tell the PVR, if people still have that because BitTorrent, but you can just tell it, I want these 3 shows. How many of you have used a tool called If This Then That, or Zapier? You don't have to teach people how to use it. It looks similar enough to things that they've seen before that they can just start scripting workflows. That's nice. How can we take advantage of it? Well, manipulating data in Scratch is really clumsy. You have to go through at least 6 motions to say x assigned x plus 1. And some typing is involved in there as well. It wasn't designed for that. It was designed for control flow of scripted objects. It doesn't have to be that way. This is Yahoo Pipes. But there are hundreds of other data flow systems that have draggable interfaces. I want this, and I want its output to go here, and then that feeds this thing, and I'm going to customize it a little bit. This happens to be a linear chain, but you can build more complex control flow graphs. And there are lots of these systems. If you're an audio engineer, your interface to complex digital audio is drag out blocks and connect them to create the data flow diagram. I worked for a while for a company called Side Effects. It builds a high-end computer animation tool called Houdini. Those of you who remember the liquid metal man from Terminator 2, that was one of our first big successes. If you're doing high-end character animation in Hollywood, you're using Side Effects, you are dragging out blocks and creating a data flow diagram and then customizing the steps. Please.
Do some of the successes of Scratch really hold to, let's say, LabVIEW or
Yep.
prints in
Absolutely.
Unreal?
Absolutely.
Because it seems like, I mean, just talking to game development environment, everyone says blueprints is terrible, and why would I do the drag and drop? Even if they don't know C++, they'd rather learn C++ because you don't have the functionality with
It's possible to build a bad drag and drop interface just like it's possible to build a bad programming language. And yet if you're an audio engineer, you're using these tools all of the time, and they are actually a lot easier than writing code. If you stay in the sandbox, these are great. If you want the flexibility and want to go out of the sandbox, sorry, I can't help you. Okay, so I'm imposing constraints. I am limiting what you can do, but as long as that's all you want to do, you can go a lot further. And I think there's a strong analogy here with Excel. Fewer than 1/10% of Excel users ever write a macro of any kind. Most people stick within that blocks and cells paradigm. There's a lot of things you can't do that way, but there's a surprising number of things you can. And I don't know the extent to which people tailor their problems to fit the tool. Whether there are business workflows that they simply don't implement because it doesn't fit naturally into the one tool that they've mastered. Okay. I want somebody to build me some Scratch blocks for manipulating tabular data. Right? You will immediately change the lives of millions of people. Okay? Blockly from Google provides the framework. The latest version of Scratch is implemented in Blockly, which itself is built in JavaScript and is available under an open license. So you can create new blocks. All right, so you've got a toolkit. You don't have to start from scratch, and it will look familiar. Deployment is a solved issue, et cetera, et cetera, et cetera. Right? How many of you use R? Okay, what Hadley Wickham and others have done in R is create what's called the tidyverse. It's a set of functions that perform stereotyped operations on tabular data. It doesn't do everything, but what it does very well and very simply. And it follows a pipeline model. Filter, select, aggregate, display. Rearrange, mutate, create a new column, merge it into this one, aggregate, display. If your statistics fits that model, it's a hell of a lot easier to use than anything else I've played with. If it doesn't, now you have to write R, which isn't a lot easier than anything I've done. Right? What we've got is both a set of verbs that we want implemented, which have been field tested over many years. We're sure that this is a good set of operations. It comes with curriculum. There's a large number of intro stats books that use this toolbox, not generic R, not generic Python or stat or anything else, but this toolbox. So we've got a set of requirements. Your blocks need to implement the exercises in this textbook. We've got a platform to build it on, and we've got millions of kids in high school who've seen this interface and don't need to be taught the interface. Crucially, deployment is a solved problem, and the numbers are running in our favor. Number of students writing the AP exams, 2012 versus 2017. Computer science has nearly doubled its numbers. That's great, but that's still not a large number. Calculus is holding more or less steady. Look at the numbers for statistics. Right? I said that we have to fit into the existing curriculum. We can't displace things. This is our opportunity. We provide people with a blocks-based interface to do high school statistics. So they're learning more computing, so that they're getting ready for this exam, so that they arrive at university already having done something that would pass for data science. I don't know what I can do with calculus as a high school student. Maybe game development, game physics, maybe. Megan Duffy at the University of Michigan has her high school students reanalyzing the water quality data from Flint, Michigan. Okay, now I have your attention. Michael Chow out in Philadelphia has his students comparing Spotify playlists. Who likes the same music I do, and what the hell are you listening to? Right? So right away we've got authentic tasks. We have things that high school students will actually care about. That's kind of cool. It's real math. I think we all agree that despite what my teachers told me when I was an undergrad, statistics is real math. Now, I had number theorists, right? We've got teachers. We've got people who are already teaching the statistics and already using computational tools of various kinds, and now we're going to make their lives easier. And one of the things, you can't see down at the footer here, statistics is an authentic task, but it's an authentic task for the teachers. How many of you are old enough to remember the early 1980s when PCs arrived in high schools? And there were classes on Logo. And by the early 1990s, after a decade passes, most of those programming classes had kept the same course code but had morphed into business skills classes. Here's how to use Excel, PowerPoint, and Word. One of the reasons for this is that the teachers themselves didn't have anything they could do in their own job with Logo. But they had to stay proficient with the office tools because they need to prepare slides, they need to prepare handouts, and they need to analyze their grades. So the tools that teachers use in their own work are things that we can build on. If I give you a simplified drag and drop interface for statistics that you can teach and also use to prepare your end of term reports, you're much more likely to stay up on it. It's not going to slip away or morph into other things. Okay? If the students are coming in with some stats, then we can start to teach them real engineering. I did an engineering degree. I don't wear the iron ring any longer, but I actually trained and certified as an engineer. I was taught that engineering is, and I quote, the use of the scientific method to analyze and design structures, devices, and systems. Instead of finding out how the universe works, you use the same methods to build new things. I want to require stats rather than calculus for entry into CS. I think this is defensible. I want to have students analyzing real software engineering data starting in their first year so they think it's normal. Here's an example of what I want. Given the source code for 6 software projects, do long functions have more bugs than short ones? Why do we teach you to modularize your code? These days the answer is because the professor said so, and marks are taken off if your function is more than 22 lines long. That's extrinsic motivation. Do it because otherwise I take grades off. Go and do the analysis and find out why we're telling you to modularize your code. It's because there will be fewer bugs. It won't convince everyone. I mean, you may not know this, but MDs in the United States are actually more likely than the average citizen to smoke, which tells you everything you need to know about human nature. But it will change some minds. As I said earlier, it requires tool use, it requires model building, it requires statistical analysis, it requires the skills that you care about. It gets students doing the science so they understand it, so that when they graduate and they're off there working in a company and we say, can we please share data with us? They'll understand the science. When we say we've got a new result that will make your programming better, they will understand and maybe believe the science. And at this point I have to back up a little bit. Prior to 1960, most of the top 20 schools in the United States did not require statistics in undergraduate life science education. Pre-med, psych, biology, you didn't have to do stats. And in fact, a lot of the universities didn't offer stats to undergrads in 1960. By 1970, all of them offered it and most of them required it. And the question is, why that decade? Why didn't that change happen in the 50s, the 70s? What was special about the 1960s? Donald Mackenzie was giving this talk, and I put up my hand and I said, well, that's when computers became available. And he said, plausible but wrong. The real reason is a generation that had encountered stats and operations research during the Second World War had aged up to the point where they were faculty. They were sitting on curriculum committees, signing off on grants. You had a cohort with a shared vision of what better looked like, getting their hands on power at the same time and able to pull in the same direction. Software Carpentry focuses on graduate students because I realized after many years that I wasn't going to be able to change the minds of enough faculty to make a difference. it is in fact surprisingly difficult to change the mind of a tenured faculty member in physics, right? What I could do was train up a generation of graduate students and then wait 15 years for them to become faculty and make the changes that I couldn't, right? The same can happen in industry. I want project managers and team leads in industry to understand that they should be reading the research summaries in the same way that MDs read research summaries. MDs read it because they've been trained to believe that the research is valuable. Okay, let's do the same for software engineers. And it fits into the existing curriculum. You know, there's the interface for first-year math. As long as there's still a course code that hasn't changed, we can do anything. All we have to do is change the content. Right? Because it's culturally defensible. Many professors in computer science will tell you that their students need more math, that they're not numerate. Great. I'm giving them a math they can use. It's called data science. Right? My ultimate goal, of course, is larger change. Female participation in computer science degrees. We all know the numbers. I don't believe my generation is going to fix this any longer. I'm 55. If we were going to fix this, we would have by now. What we can do is raise up a generation that will. So I'll show you one of the other exercises I would like to use in an undergraduate software engineering course. I taught for 3.5 years at the University of Toronto. Every year, like clockwork, a message would pop up on the undergraduate bulletin boards. Why are there so few girls in our classes? And somebody would immediately reply, well, studies show women don't like math, women aren't good at it, et cetera, et cetera, et cetera. The studies were never cited, but they were quoted. Okay, I got tired of this, and it was my last semester teaching, so what the hell? 10% of the grade in every course at the University of Toronto has to be written work. So this was the essay question for 10% in my senior software engineering course that year. More than half of the male students in the class chose to take the 10% hit rather than submit an answer to this question. Mission accomplished. Because that was the follow-up. Multiple studies have shown that if you're trying to teach ethics and you're teaching it in the abstract, it has no effect on behavior. Everybody knows what the right thing to do is if you're the engineer and that's the challenger and you know that the O-rings have problems. You give the answer that the instructor wants. Making people uncomfortable changes their behavior. Asking people to go and dive into data and cite sources and answer questions like these and then say, oh, and how does this connect with this thing that I just posted on the undergrad bulletin board? That's going to move the needle. But in order to do this, I need an audience that actually understands that data matters, that evidence matters. Right? So yes, this is social engineering. Completely, absolutely, explicitly social engineering. Because we've got big problems to solve. I have in Ontario a premier. Rob Ford's older brother is now premier of Ontario. The man is a thug who used to sell drugs out of his backyard. He has just scrapped the carbon limits in Ontario. It's going to cost the province $3 billion in fines because of various bilateral arrangements, but he does not believe global warming exists. Never mind man-made, he just doesn't believe it's happening. I want people to pay attention to science because the only things that are going to get us through the next 50 years are more science and more courage. And if they're not listening, what's the point of doing the science? I can't fix everything, but if I can get programmers to take data seriously, the world's a slightly better place. And I think that's the hard-boiled egg. I think that's an achievable goal. So, if this isn't a big enough project and you're looking for others, I actually keep a page on my website of projects I'm never going to get around to because I don't have time, but I'm happy to try to talk you into them. I actually do run a 1-hour seminar on how to talk people into things. Okay? My dad was my English teacher for 5 years in high school. I grew up in a little town on Vancouver Island. The other English teacher wasn't sober very often, so he just arranged things. And my daughter is now programming in Scratch and wondering why she can't use Scratch to program Minecraft. Why she has to go and write this text stuff, which is just so obviously broken, when all she wants to do is make blocks jump over people. That was the genesis for this talk. I'm hoping that one of you can solve that problem. Whole talk is available online. There's the URL. There's how you reach me. Here's some of the books that have shaped my thinking on this. And we've got 12 minutes for questions. Thank you very much. Please.
Comment? Yes, it's social engineering, but I would say you're proposing a theory of social engineering rather than, it's like one possibility, right? But I have a different question. So what is the role of fundamentals in your pedagogical schema? So, can I
Please.
So it's, I heard, what's learning multiplication or division, or I heard why curly brackets in people's lives. But let's instead hit at a higher. Let's hit at a higher level of abstraction layer and say people plug in numbers into a statistical operation. So where is the role of understanding what a regression is rather than plugging it into this thing? What is the role of understanding computational operations,
sure.
fundamentals, rather than at the abstraction layer?
Sure. So the question, this is for the recording in the camera. The question is, what's the role of fundamentals and abstraction in this? A very powerful evidence-based teaching technique is sometimes known by the acronym PEAT: problem, example, theory, elaboration. Why do we care? So that you're intrinsically motivated to learn. Then you work through a specific so that people have an idea of what this is. Then you give them the general theory, so that now they've got something concrete to relate it back to. Novices won't understand the abstraction because they don't know what it's abstracting from. Then you elaborate by giving them at least one more example so they can see what are the intrinsic features as opposed to the accidental features of the example. Okay? That's a sequence that I'm very happy with. I think that we start by saying to students, here's how to tell if your Spotify playlist is like somebody else's or different, or who in the class are you similar to. Okay, how did that work? Let's take that apart and see what the math inside that is. But now we've got you hooked. Now you can see what the application is. If we come back to the work of Gusdeel and Erickson at Georgia Tech, giving people authentic tasks early on in their computing education significantly increases retention. The theory-first approach works for people who've already understood it, and for the 15% of the population who are autodidacts. For the other 85%, I have to show you the why and the how, and then I can say, now here's the generalization so that you can solve all of these other problems. I'm not proposing that we eliminate theory. I'm certainly not proposing black box machine learning, which is, I have TensorFlow, I can solve the world. All I have to do is feed in data, right? I am proposing that we try to connect it with the students' lives as early as possible and in as concrete a way as we can, because it works better pedagogically. Okay? Other questions? Please.
In my experience working with scientists who are trying to become data scientists, they had some of the same approaches as software engineers have towards interfaces. They think that GUIs are not cool, and so they don't want to use them because they're sort of usable, right? So how do you social engineer that community into a different perspective?
So the question is, how do I socially engineer people into using tools that are usable? Organizations much older than computing have spent a couple thousand years trying to teach people humility and compassion, right? Hasn't worked very well. What happened with software carpentry was that for years I was trying to teach people to do the right thing because if you don't, it might be wrong. They didn't show up for workshops. In about 2010, I switched tracks and said, do it this way because it's more productive. You'll be finished sooner. How many of you have seen, and then they started showing up in bulk. How many of you have seen a tool called OpenRefine? OpenRefine is a beautiful piece of software if what you've got is messy data that needs cleaned up, right? It's an example of something that even power users will pick up because it's just easier. And the fact that it doesn't force you to choose between a GUI and scripting, that it gives you a ramp rather than a cliff. I'm upset with many of the tools that we use because we keep putting our users in front of cliffs. How many of you use Microsoft Word? Be honest, it's nothing to be ashamed of. We're an open, inclusive community. Okay? How many of you use Excel? Okay? The single biggest thing you could do to improve practices is make version control work with the Microsoft Office formats. Because right now you are telling everybody who has learned how to create a paper or how to analyze data that they have to throw away all of the tools they know and switch to things that are demonstrably more clumsy. You have to use Markdown and then compile your document. Oh, and you need to embed some LaTeX. The response from any intelligent, well-balanced person with an ounce of self-respect is, what the hell? Right? Why should I have to throw away 30 years of advances in user interface in order to use Git? The answer is because I'm a programmer. Right? And I don't care about anything that cannot be edited with VI. Right? And yet, I had an estimate from some people on the LibreOffice team. They thought it would take 3 engineers 8 months to repurpose LibreOffice to give you a 3-pane diff and merge view for Word documents and Excel spreadsheets. And then all of a sudden, everybody that we're working with who's comfortable with those doesn't have to throw stuff away. They can migrate. They can climb a ramp instead of a cliff. And we haven't done it, I think, because of Stockholm Syndrome. Right? This hurts so much that I have to keep doing it, otherwise I'd have to admit to myself that that pain was for no purpose at all, and then, well, it's just not acceptable, right? I'm quite serious. If any of you want to bring another 1 million people into data science, teach Git and other version control tools to handle the file formats that they're using. How many of you use the Jupyter Notebook? Okay. Frequent conversation. This is the Jupyter Notebook. It's good. You should use it. Thumbs up from students. This is version control. It's Git. You should use it. Thumbs up from students. And now we put the O. Right? 4 years ago, a team of students that I was working with in Montreal built a 3-pane diff and merge tool for the Jupyter Notebook that actually worked. You could say git diff something.ipynb, and it would pop up yours, mine, and the merge, and you could drag cells around, and it just plain worked. It was online at nbdiff.org, and it got no traction at all. People seemed to want to diff 160 kilobytes of base64 encoded PNG by hand. I don't get it, right? We have all the technology we need, folks. We just need to make the technology more approachable. We need to stop excluding people. And every time we build something that's needlessly complicated, we are excluding too many people. Other questions, if I haven't scared you? Please.
I'm curious as to what you think about changes that need to be made in basic statistics education. Because in my experience, the sole statistics class that I had to take for computer science at my undergraduate university, it was a lot of dredging through basic, mean, median mode, and yep. My classmates were struggling through it. They were, pretty smart in other courses, but for some reason they hit the statistics. It's like they fell apart.
There are people in this room who are far better qualified to answer that question than I am. I know about computing education. I'm a consumer of people who've had stats education. I know there's a lot of discussion about how to reframe it both around more modern methods and around the ubiquity of cheap computing and the availability of real data sets, real large data sets, right? I don't know enough about this to have an opinion. Lots of people here could, right? Going once? Going twice? Thank you all very much.